Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the capacitor. Our objective is to introduce the capacitor. We'll examine the basic construction of a capacitor, the units of capacitance and those properties that influence capacitance, interpreting and measuring capacitor values, and capacitors in series and in parallel. Capacitors are electrical devices that can both absorb and return a measurable quantity of electrical energy to a system. Capacitors store energy by accumulating charged particles on two conductive plates separated by a small gap. The gap is often filled with an insulating, i.e. non-conducting dielectric substance such as mica, ceramic, oil, paper, or a paste-like or liquid electrolytic compound. All these substances sandwiched between these conductive plates are assumed to be non-conductive in ordinary working conditions. The schematic symbol for a capacitor hints at the internal construction of a capacitor, being two parallel lines. These parallel lines symbolize the parallel plates with a small gap between the plates. You may also see capacitors represented schematically as a straight and curved line for reasons I'll explain in a moment. On a very basic level, a capacitor is a charge storage device, and a capacitor's ability to store charge is measured using a capacitance figure measured in units of farads. Capacitance is charge per unit volt. The concept of capacitance is symbolized using the letter C, and the units of capacitance are in farads, symbolized using an F. A farad is therefore a derived unit where 1 farad equals 1 coulomb of electrical charge stored per volt. It should be noted that the concept of charge is symbolized as a Q. Don't ask me why, and the units of charge is the coulomb, also symbolized as a C, where 1 coulomb of charge is equivalent to a group of 6.24 times 10 to the 18th charged particles. This choice of nomenclature is somewhat problematic because the concept of capacitance and the units of charge are both represented using the letter C. To prevent yourself from confusing the two, I typically write the concepts followed by the appropriate unit in parentheses. In summary, capacitance C in units of farads F is equal to charge Q in units of coulomb C per volt V in units of volts V. Trust me, I feel your pain, but that's the way it is. Let's examine a couple derivations of this relationship. Consider a capacitor full of 6.24 times 10 to the 12th electrical charges at 1 volt. Given 1 coulomb of electrical charge is a collection of 6.24 times 10 to the 18th particles, this represents a charge of 6.24 times 10 to the 12th over 6.24 times 10 to the 18th, or 1 microcoulomb of charge. This capacitor therefore has a capacitance value of 1 microcoulomb over 1 volt, or 1 microfarad. This might seem like a small capacitance value. However, understand that most commercially available capacitors are manufactured inside the picofarad to microfarad range. Consider the same 1 microfarad capacitor at an increased voltage of 25 volts. What happens to the charge inside this capacitor? Will it go up or will it go down? An algebraic rearrangement of our three-variable capacitor equation suggests that volts times capacitance equals charge. Substituting in our given values of 25 volts and 1 microfarads, we find that the same capacitor now stores 25 microcoulombs of charge, for a total of 156 times 10 to the 12th individual charges, 25 times as much as it did at 1 volt at 25 times the voltage. It makes sense. Let's consider another implication of this second algebraic manipulation. This derivation also suggests that a capacitor with a large capacitance value will store more charge at a given voltage than does a capacitor with a smaller capacitance value at the same voltage. Consider a 4.7 microfarad capacitor, also at 25 volts. This analogy may or may not be helpful. However, if you've got an understanding of hydraulics, capacitors are often like to accumulators in hydraulic systems, where an accumulator is a vessel full of pressurized fluid. Accumulators in hydraulic systems augment flow and stabilize the system by absorbing any sudden changes in pressure. Depending upon the application, capacitors might be included inside an electrical circuit to perform quasi-equivalent tasks. Consider this simplified buck chopper circuit, a power electronics device that steps down DC voltage. The moment the switch closes, current rushes into the system, a portion of which charges up the capacitor. The moment the switch opens, the DC source ceases to provide current to the system. However, the charged capacitor can now discharge itself into the load resistor. When this switch is closed and opened repeatedly, resistive load in effect sees not on again and off again pulses of full current, but rather a relatively constant steady-state value. Returning to our hydraulics analogy, an accumulator with a larger volume can hold more pressurized fluid, and similarly, capacitors with larger capacitance values can hold more charge. Consider the size differential of a 3,300 microfarad capacitor and a 100 microfarad capacitor of similar construction. It makes sense that the 3,300 microfarad capacitor is substantially larger than the smaller 100 microfarad capacitor since it is intended to hold more charge. Depending upon the construction method and the material properties of the capacitor in question, this direct means of size and capacitance comparison doesn't always hold true, but for now just go with it. A larger vessel can hold more charge and a smaller vessel can hold less. A capacitor is a vessel into which you can stuff charges and at a later time withdraw them. This being said, note that capacitors include a small gap between the plates. As you are no doubt aware, current does not flow through an open. You might therefore initially assume that a capacitor blocks current flow. However, we'll learn that an uncharged capacitor experiences a brief surge of incoming displacement current during the charging process as charges accumulate on the plates. Additionally, a charged capacitor can supply a momentary burst of outgoing displacement current as charges are shed from the plates during the discharge process. We'll examine how the electrical properties of the circuit under inspection influence the intensity and duration of these bursts of current during the charge and discharge process in the very near future. Let's review our understanding of electrical charges. As you're no doubt aware, there exist both positive and negative electrical charges, and the ratio of these two charges influence the charge state of a larger object. Charged objects interact with other charged objects in a very predictable manner. The classic diagrams describing this behavior being two positively charged socks pushing each other away, two negatively charged mittens pushing each other away, and one positively charged sock and one negatively charged mitten pulling each other close. A capacitor in a discharged state is an empty vessel. This does not mean it's empty of charges, however. A discharged capacitor is electrically neutral because there exists an equal number of positive and equal number of negative charges on both plates. As such, there is no charge imbalance and there exists no voltage differential between the plates. If, however, there exists a surplus of positive charges on one plate and a surplus of negative charges on another, this capacitor can be said to be charged. The charge imbalance between the plates of a charged capacitor establishes a resulting voltage differential. Understandably, the greater the charge imbalance, the greater the voltage between the plates. It can be said that charge concentration directly influences voltage. More charge, more voltage. Less charge, less voltage. Theoretically, an ideal charged capacitor will maintain this charge imbalance indefinitely because the non-conductive insulating dielectric inside the gap between the plates prevents current flow and charge equalization. In practice, a real capacitor will exhibit a tiny amount of leakage over time and cannot be expected to maintain a charged state indefinitely. For now, let's just assume this is an ideal capacitor and no leakage occurs. As with all charged objects, an electrostatic field develops between the oppositely charged plates. The electrostatic field is normal to the plates, except for a negligible amount of fringing at the edges. The electrostatic field between the two charged plates is measured in units of volts per meter. Several conclusions can be made from these observations and our previous understanding of capacitance. Given the quantity of charge directly influences voltage, we could state that a large number of charges will result in a larger voltage differential, and given a larger voltage differential, we should observe a stronger electrostatic field. It makes sense. More charges, more voltage, stronger field. Coming at this from another direction, given quantity of charge directly influences voltage, we can state a smaller number of charges will result in a smaller voltage differential, and given a smaller voltage differential, we should observe a smaller electrostatic field. It again makes sense. Less charge, less voltage, weaker field. Other conclusions can be made. Notably, distance inversely affects the electrostatic field. Given a constant voltage between the two plates, it should be noted that by moving them further apart, we will lessen the electrostatic field. Conversely, moving the plates closer together increases the electrostatic field. This should make sense given your experience around charged objects. The electrostatic field around a charged wool sock, freshly pulled from a dryer, exerts itself quite strongly up close, but cannot be felt from across the room. In summary, more distance, weaker electrostatic field, less distance, stronger electrostatic field. An important observation can be made about the limitations of capacitors at this point. First, the electrostatic field in units of volts per meter places an upper limit of voltage that can be safely applied across any capacitor. If the electrostatic field ever exceeded the breakdown strength of the insulating material inside the gap, whatever is inside the gap can become a conductor and bridge the two plates. Accompanying this breakdown event is a large arc of current which equalizes the charge, often destroying the device in the process. As such, capacitors often state a maximum safe working voltage under which the capacitor will function as intended, and above which catastrophically, sometimes explosively fail. Consider this capacitor with a safe working voltage of 25 volts. At 25 volts and below, things are just fine. When I crank it up to 85 volts, things go south rather quickly. Another practical limitation of capacitors is the quantity of space available for charges on the plates. Charged particles take up physical space like passengers on a bus, and at a certain point the bus is full and there simply isn't any room for more charged particles. One way of increasing the charge storage ability of a capacitor is to simply increase the area of the plates. Larger plates result in more functional surface area and thus an increased ability to store charges. Conversely, smaller plates result in less functional surface area and thus a decreased ability to store charges. This supports our earlier observations that given capacitors of similar construction and material properties, the physically larger capacitor can store more charges at a given voltage and the smaller less. Finally, the influence of the dielectric material properties inside the gap on capacitors cannot be neglected. As we demonstrated, charged particles accumulate on the plates of a charged capacitor. While the insulating properties of the dielectric material does prevent current flow from one plate to another important phenomenon occurs. As we observed, an electrostatic field is established between the charged plates. Depending upon the material properties of the dielectric being employed, it can assist or permit the establishment of the electrostatic field through it in the following fashion. The dielectric, being electrically neutral, consists of equal number of positive and negative charges. The positive charges on the top plate attract the negative charges inside the top layer of the dielectric, and similarly the negative charges on the bottom plate attract the positive charges inside the bottom layer of the dielectric. As a result, an electrostatic field establishes itself internal to the dielectric, opposite of the electrostatic field established between the plates. Because of the dielectric influence internal to the capacitor, external to the capacitor, it appears as if a number of charges on the plates have found an equal and opposite dance partner. And as a result, more charges can accumulate on the plates at a given voltage. In summary, functional area of the plates, material properties of the dielectric, and the distance between the plates all affect a capacitor's capacitance value in the following fashion. A capacitor's capacitance value in units of farads F is equal to the functional area of the conductive plates A in units of meters squared times the relative permittivity of the dielectric in question, mu r, a dimensionless constant, times the permittivity of free space, mu 0, in units of farads per meter, divided by the distance between the plates, d, in units of meters. In terms of units, it makes sense. Meters squared times farads per meter divided by meters equals our resultant capacitance in units of farads. Before we make use of this equation, let's discuss permittivity and relative permittivity. Permittivity is an experimentally determined material property that quantifies how easy it is to establish an electrostatic field inside the material in question. The permittivity of free space has a value of 8.85 times 10 to the negative 12 farads per meter, meaning for every meter vacuum you cross, you get a capacitance value of roughly 8.85 times 10 to the negative 12 farads. Substances like mica have a permittivity that is 5 times stronger than that of free space, meaning the electrostatic field can be established inside mica 5 times easier. The relative permittivity, mu r, of mica is therefore 5. Get it? Mica permits the establishment of an electrostatic field 5 times better than vacuum, so mica's permittivity is mica's relative permittivity times the permittivity of free space, or 5 times 8.85 times 10 to the negative 12 farads per meter, or 44.3 times 10 to the negative 12 farads per meter. Other substances have different relative permittivity values. Consider a couple common dielectrics employed in capacitor construction. Oil can have a relative permittivity of 4. Porcelain can have a relative permittivity of 6. Tantalum oxide style capacitors can have a relative permittivity of 30. Ceramics, depending upon composition, exhibit a wide range of relative permittivity, with some ceramics having a relative permittivity of up to 7,500. Given our capacitance construction formula, it makes sense that if you wish to make a larger capacitor, you'd make the plate's functional area as large as possible, make the plates as close as possible, and stuff it full of some exotic ceramic with a high relative permittivity. Consider a capacitor with square plates having a side length of 2.54 centimeters or 0.0254 meters, roughly an inch by inch for the ignorant savages scavenging trash in the wasteland. This represents a functional surface area of 0.0254 times 0.0254 meters, or 645.2 times 10 to the negative 6 meters squared. Let's say the plates are separated by a distance of 1 millimeter, or 0.001 meters, and the space between the plates is filled with mica having a relative permittivity of 5. What's the capacitance of this capacitor? Substituting our given values into the capacitance construction formula, we arrive at a capacitance value of roughly 28.5 picofarads. What if we wanted a larger capacitance value? However, we're restricted to the same size package. Really, our only option is we'd have to swap out the mica dielectric for something with a larger relative permittivity. Let's say we employ tantalum as our dielectric. Substituting in our new relative permittivity value of 30 into the capacitance construction formula, we arrive at a capacitance value of 171.3 picofarads, 6 times the capacitance of the capacitor employing the mica dielectric, and 30 times the value of a capacitor made strictly with a vacuum between the plates. It makes sense. See if you can calculate the property of interest through the following capacitor combinations. Our first example asks us to calculate the capacitance of a capacitor with super large plates having the following dimensions: 5 centimeters by 15 centimeters, separated by 0.5 millimeters. Yes, you heard me right, 5 centimeters by 15 centimeters. Obviously, it'd be super hard to work with a device of these dimensions. For this reason, capacitor plates aren't necessarily square plates, but rather a long strip rolled into a cylinder, allowing the same functional surface area in a much smaller and more manageable package. Let's say it's filled with a dielectric that happens to have a relative permittivity of 30. Our second example asks us to determine the dielectric being employed inside a 128 picofarad capacitor with tiny circular plates having a diameter 0.7 millimeters separated by 0.2 millimeters. This will take some algebraic manipulation and knowledge of circular area calculations. By all means, pause the lecture and try these examples on your own. If you're struggling with the second example, here's a hint. Solve for relative permittivity. Here's another hint. Circular area is pi over 4 times the diameter squared. Use of these hints is admission of weakness on your part. If you're tracking, you should have arrived at the following values. For our first example, this capacitor has a functional area of 0.05 meters times 0.15 meters, or 7.5 times 10 to the negative 3rd meters squared. The plates are separated by a distance of 0.0005 meters. The dielectric has a relative permittivity of 30, and the permittivity of free space is a value of 8.85 times 10 to the negative 12 farads per meter. Substituting our given values in the capacitance construction formula, we arrive at a capacitance value of approximately 4 nanofarads. Which brings us to a rather interesting challenge. Go to the stockroom and find a 4 nanofarad capacitor. Chances are you'll be looking for a long, long time because there is no such thing as a 4 nanofarad capacitor. For reasons that are completely beyond me, capacitor manufacturers only state capacitor nominal values in units of microfarads or picofarads and rarely, if ever, state the nominal values in nanofarads. This 4 nanofarad capacitor would therefore most likely be labeled as having a nominal value of 4,000 picofarads. Long story short, microfarads or picofarads only. I don't like this any more than you, but we're stuck with it, so we may as well get used to it. Moving on. For our second example, we've been asked to solve for the dielectric substance between the plates for a 128 picofarad with known dimensions. An algebraic rearrangement of the capacitor construction formula, solving for relative permittivity, suggests that relative permittivity is equal to the capacitance times the distance divided by area times the relative permittivity of free space. If this capacitor has a diameter of 0.7 millimeters or 0.0007 meters, it has a functional surface area of pi over 4 times the diameter squared, or roughly 384.8 times 10 to the negative 9th meters squared. Substituting our given values into the algebraic rearrangement, we arrive at a relative permittivity of 7,516. Most likely, some type of ceramic is being employed as the dielectric of choice for this capacitor. As I stated previously, capacitor manufacturers typically state the nominal value of capacitors in units of microfarads or picofarads only, and never state the nominal value in nanofarads. Because this will be an issue in the future, let's get some practice dragging this ball and chain around and smiling while doing so. Let's say you're presented with 3 capacitors having the following values: 0.1 microfarad, 0.068 microfarads, and 1,800 picofarads. Determine the equivalent capacitance value for these capacitors in units of nanofarads. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following conclusions. The 0.1 microfarad capacitor is equivalent to 100 nanofarads. The 0.068 microfarad capacitor is equivalent to 68 nanofarads. Finally, the 1,800 picofarad capacitor is equivalent to 1.8 nanofarads. Let's do the same exercise in reverse. Let's say you need a 33 nanofarad capacitor. However, you're presented with the following available options: 3.3 picofarads, 33 picofarads, 330 picofarads, 3,300 picofarads, 0.033 microfarads, 0.33 microfarads, 3.3 microfarads, 33 microfarads, and 330 microfarads. Which is the correct capacitor? By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following conclusion. The 0.033 microfarad capacitor presents the desired capacitance value of 33 nanofarads. The 3,300 picofarad capacitor would be 3.3 nanofarads, too small, and the 0.33 microfarad would be 330 nanofarads, too large. Again, I don't like this choice of units any more than you, but we're stuck with it and you simply gotta get used to it. If you're struggling with this concept, I'm suggesting you revisit the Engineering Prefixes lecture available at the Big Bad Tech channel.